easier to tell them apart. So what you can see from all this is that there's clearly no one frequency that's best for all applications. Higher frequencies in general are better for smaller objects, less conductive objects, and lower frequencies give an advantage on things like copper and silver coins, large, very conductive objects. Okay, now this brings me to the DFX and what specifically it offers in the way of new features and capabilities. The DFX transmits and receives simultaneously at these two frequencies, 3 kilohertz and 15 kilohertz. And what makes it unique is we have each of these frequencies available independently, and we can select either one and process signals in the manner in which we've successfully done it for many years by doing ground balancing, discrimination, etc., at either frequency. So the operator can select whichever one he feels is more appropriate for the kinds of targets he's looking for and the ground conditions and such. But in addition to that, the DFX can process both frequencies of information simultaneously. And the way we do that is by first processing them in a conventional fashion. So for example, we'll do discrimination at 3 kilohertz by conventional means. We'll also do discrimination at 15 kilohertz by conventional means. And then our microprocessor will compare the results. And there's a couple of ways that we do this. The first way is to look at the strength of the signal at either of the two frequencies and to pick the stronger of the two. So I'll give an example of that. If a nickel, for example, at 3 kilohertz has a fairly weak signal, and at 15 kilohertz the signal is much stronger, the microprocessor can look at both channels of information and select the strongest signal, which in this case would be 15 kilohertz, and then report that signal to the operator in the form of a VDI number and an audio response. On a silver dollar, on the other hand, at 3 kilohertz, the signal is farther away from the ground axis and therefore gives me a stronger response. So the microprocessor in this case would choose the 3 kilohertz data and report that to the operator and use that one in determining the VDI number. And we call this mode the best data. Where the processor picks the strongest of the two signals. Now, something I should probably mention at this point is what we call normalization. If I pass over a nickel, for example, at 3 kilohertz, I'll calculate a phase and a VDI response that will be at 3K, maybe 10. If I do the same thing at 15 kilohertz, I'll get a VDI response that might be 35. And what the processor has to do in order to be able to perform this operation and have the resulting display make sense to the operator is to convert those numbers to more familiar units. And since on a detector running at 6.6 kilohertz, nickels come in at about 20, the processor then takes the 3 kilohertz data, does a mathematical operation, and shifts that VDI result of 10 and makes it 20. At 15 kilohertz, it takes the result of 30, rotates it backwards, and again causes that to read out as 20. So for the operator, it doesn't matter which frequency you pick, the nickel will always give you a VDI reading of 20. And that is something that can be turned off by an advanced operator if you want to see the original numbers. But that brings me to the next two-frequency mode of operation, which we call correlation. If I pass over the target and the determination at 3 kilohertz gives me a result of 20 after I've done the normalization, at 15 kilohertz, if it gives me a result of 20, then I've got a pretty high degree of confidence that that reading is correct. And I'll report that to the operator on the screen in the form of a VDI number and an audio response. If, on the other hand, the results from these two operations don't agree, for example, if at one frequency I get a reading of 10 and at the other frequency I get a reading of 40, that reading will be suppressed. And again, we call this correlation. And these are two of the operating modes that the operator can select. So far we have 4 different operating modes. You can select 3 kilohertz single frequency operation, 15 kilohertz single frequency operation, best data mode, or correlate mode. Okay, one thing I want to mention in passing is that the normalization feature, which again is intended for a more advanced operator, can be turned off, and there's a reason you might want to do that. As I mentioned earlier, for example, at 3 kilohertz, targets tend to crowd together in this neighborhood. And if you turn the normalization off, you can see at the other end of the scale, the targets in the silver coin and copper coin range will spread out nicely, and you can see that a lot better if normalization is turned off. If you select 15 kilohertz as your operating frequency, then as these targets begin to spread and move out in this direction, again with normalization turned off, you get a lot finer resolution, and you can see the numbers at either end of the scale more clearly. So we think that'll be of some use in the field. Now, so far I've been talking strictly about discrimination and target ID modes of operation, but I want to talk a little bit about the all-metal mode. I started out earlier by drawing salt up here. In a conventional single frequency metal detector, I can be balanced to the ground or I can be balanced to the salt, but I can't be balanced to both at the same time. So consequently, if you go to the beach and you balance your detector to the black sand, you're going to be very sensitive to the salt. If you balance to the salt, you're going to be very sensitive to the black sand. And the DFX has something very useful, which is a 2-frequency all-metal mode of operation. And what we do there is we balance the 3 kilohertz signal to salt. We also balance the 15 kilohertz to salt. Now both of them are sensitive to normal ferrous ground or to black sand. But by doing an appropriate scaling and subtraction operation, we can get black sand or ferrous ground cancellation and saltwater cancellation simultaneously. So what you'll find is you take the DFX to the beach, balance to the dry black sand, begin to move down to the saltwater, and the detector will remain balanced all the way down the beach. And this is, of course, a very big advantage in all metal in terms of being able to pinpoint targets, measure their depth, and so forth. But it's also an advantage in your discriminating modes because we're using the all metal data to signal to the discriminator the appropriate times to make the target ID calculations. So it should be an advantage in both discrimination and all metal operation on the beach. Okay, so just to kind of wrap this up and summarize, what we've done here is to build a metal detector that can be operated at either of 2 frequencies in order to allow the operator to pick the one that's best for his application. Or we allow the microprocessor to look at both sets of data simultaneously and pick the most appropriate, as well as having the ability to remain balanced to dry sand and salt water all the way up and down the beach. And I think the combination of these things is going to make this an extremely powerful detector in the field.
I'm Ken White, president of White's Electronics here in Sweet Home, Oregon.
Ken White makes metal detectors. Ken and his dad virtually reinvented the modern metal detector.
Electronics was always Father's hobby, and we started during the uranium rush, and he didn't like the Geiger counters that were built at that time, so he built one of his own, and everybody seemed to want one, so he started manufacturing them.
Ken not only makes metal detectors, he uses the detectors that bear his name. Now just think about that. What if you sold a product all over the world and it had your name printed right on it? You'd make darn sure that product was as good as it could be, wouldn't you? These detectors are not called the Prospector or the Treasure Finder. They're White's detectors. And Ken is proud to have his name on every detector that leaves his factory. And before Ken asks you to use one of his detectors,